now that you are introduced to the course, there is finally time to really start creating models by yourself. In this video, we will explain the first step in the model development: translation of the research question to a conceptual model. The goal is to come up with a flow scheme or a diagram which synthesizes the relevant components and processes in the system. First, we introduce the different components of a model and explain how to visualize them in a diagram. State variables are depicted in rectangles. For instance, we can consider dissolved ammonia, biomass of algae, and free-floating detritus as the state variables in the model. Processes that transfer mass or energy between state variables are depicted with solid arrows. For example, an arrow can indicate the process of assimilation of nutrients by the algae, so the photosynthetic primary production, the process where the algae die and become detritus, and the process where the detritus is remineralized and the nutrients are released back to the original pool of nutrients. Physical transport, such as water flow or diffusion, is a process as well. This is because transport can result in the transfer of mass or energy within the system or between the system and its surrounding. Therefore, transport processes are also depicted by solid arrows. In our example, transport processes that influence the nitrogen balance in the system can include import of ammonia from agricultural runoff, or export of ammonia, algal biomass and detritus via water flow. When external forces influence a process, we use dashed arrows. For example, light is an important external factor that influences the assimilation of nutrients by the photosynthetic algae. Derived quantities, which are calculated from the state variables, are depicted with circles. An example would be a chlorophyll concentration, which is a measure of the algal biomass that can be determined experimentally. Finally, the model domain is represented by a box that encompasses all the components mentioned before. Another example of models that we will study in this course involve chemical reactions. Generally, a chemical reaction where A and B reacts to C and D can be written as shown below. Here, the Greek letters alpha, beta, gamma and delta are the stoichiometric coefficients which tell us how many moles of A and B react and how many moles of C and D are produced. This reaction can be represented in a schematic diagram shown on the right. Here, the solid line represents the process, so the reaction, and the Greek letters indicate the stoichiometric coefficients. In addition to model components such as state variables and processes, the first step of the model development needs to identify the appropriate temporal and spatial domain of the model, conditions at the domain boundaries, the so-called model currency, and very importantly, the units of each state variable. In the simple lake ecosystem model mentioned before, it is natural to express the ammonia concentrations in moles of ammonia per liter of water, while the algal biomass can be expressed in milligrams of chlorophyll per liter of water, and the free-floating detritus can be expressed, for example, in milligrams of carbon per liter of water. However, to simplify the model development, it's often better to use a common currency for all state variables. In this example, we are interested in the flow of nitrogen in the lake ecosystem. Therefore, the best approach is to express each state variable in moles of nitrogen. And because all state variables represent the amount of nitrogen per volume of water, all of them can have the same unit, moles of nitrogen per cubic meter. However, we emphasize that state variables do not need to be expressed in the same currency or have the same unit. We will talk more about this later when we deal with mass balances, but a good example involves chemical reactions. When modeling chemical reactions, it is better to express each chemical species in its natural unit. For example, moles of A per liter of water for species A, moles of B per liter of water for species B, etc. An example of a more complex, fully developed conceptual model can look like this. Here, the lake system is represented by the box, with smaller rectangles representing the state variables that encapsulate the modeled nitrogen compartments in the system. These include dissolved ammonia in the water column, nitrogen concentrations in the main biological trophic compartments, and free floating detritus. Solar radiation drives ammonia uptake by phytoplankton. The total level of chlorophyll is derived to link the ecosystem state to aerophotography observations from which chlorophyll can be measured. The ecological interactions, quantified as fluxes of nitrogen between the compartments, are depicted by arrows 1 to 9. Additionally, arrows indicate the input and output of ammonia into the system at the domain boundary via transport processes. The model currency is nitrogen, and the state variables are expressed in moles of nitrogen per cubic meter of water. The models are expressed on the scale of the entire lake and on the scale of years.